All right, folks, welcome to Remote Learning 21, Part 1, and I'm going to continue on with some more advanced problems involving centers of mass. Okay, so we did this one-dimensional rod of no weight scenario, and essentially that was a point mass argument. You might have picked up on this as you did a couple of those problems. It really is a weighted average when you find the x bar and the y bar on those point mass scenarios. Now, then, we also did a couple of problems involving variable densities along a rod. Okay, and then we moved on to a two-dimensional problem where there was uniform density, and we had to start to wrestle around with these strange a sub x, a sub y, and a sub z components. So I just want to spend a little bit of time here before I go on to the three-dimensional scenario. And what I just want to point out is that when you go on to the three-dimensional scenario, then we'll be using ax, ay, and az. And I just want you to see that they represent a one dimension less, right? So when it's a three-dimensional object, then a sub x is the area of a slice perpendicular to the x-axis, and so forth with ay and az. And then when you have a two-dimensional case, then a sub x and a sub y are one-dimensional objects. They're just lengths. Okay, so I'm going to make reference to that as I do the problem, and pay careful attention to that when I start talking about the units, the unit breakdown. I really think it helps to think about units as you think through what these integrals represent. All right, so it would be a shame if you just tried to utilize the formula and let it do its thing without thinking about what the components represent. Especially true as you warm up to new topics like center of mass. Okay, so there's going to be two problems. There's this problem here, which is going to be a hemisphere, so half of a sphere. And we will break this one down and find the center of mass of a hemisphere. And then there's this problem, which sort of harkens back to solids of revolution. We're going to be rotating a region around the x-axis, generating a strange solid, and then find the center of mass of that object. Okay, so let's see. Yeah, let's get into it. Okay, so this is a three-dimensional scenario, and I'm going to draw this one out the best that I can. I'm going to do it so that the xy plane is the bottom surface, and then the z-axis will be moving in the upward direction, and then I'll draw my sphere that way. All right, so let's see what I can do to make a decent drawing. All right, so I said I was going to have that x-axis and the y-axis be like the floor, and the z-axis moving in this upward direction. So let's get those labeled, and then I'll draw my sphere. We'll see how that turns out. I think I can use some pretty good tools here. So let's see. Going three-dimensional on a sphere. Let's go like, I'm going to make it all centered in just a second, but something like that. And then let's get a little tool here to help with the arc. Whoa, this is working out better than I thought. Okay, so there is my hemisphere. Is that good enough? Okay, cool. Other than I like the way that's centered. But Okay, good. Do it like that. And okay, I'll be done building it in just a second. Let's give this a few properties. Let's give that just a different color. Okay, so that's my hemisphere, and then I'm going to get in to finding its center of mass. All right, now the center of mass comes with a lot of components. So we can pull out the formula, and I'm going to need, let's see, x bar by symmetry is 0. Let's get these symmetry ones. So by symmetry, x bar is 0, right? I mean, it's going to be balanced at this point. And for that matter, y bar too is 0. So we're really just after z bar. Okay, so let's get the formula for z bar. And z bar is equal to, I mean, sort of, conceptually, it's the sum of the moments divided by the sum of the masses. I guess you could just call that total mass. Okay, but it does have this density that is lowercase d. All right, so by formula, then I have that z bar is equal to, and let's do this total mass first. The total mass is the integral of density times this a sub z of z dz. Okay, and we'll get into what the units are in just a second. Let me not get sort of derailed by that at the moment. Okay, so why does this make sense? Okay, well, this is that part where I want you to just think about the units involved. Okay, so density would be something like grams per cubic centimeter, right? Because this is a three-dimensional object. All right, but then the a sub z of z, that would be measured. That's going to be the area of a particular disk that's going to show up here, okay? But we talked about how that's going to be an area just a minute ago, so that's going to be in centimeters squared. And then dz, in just a minute I'll draw it, it's going to be some very, very small change in z, and so that's going to be in centimeters as well. Okay, so if you look at the unit analysis, you're going to wind up with grams. All right, well, that's a mass, so that's great. That's what we want to have happen. Okay, now as for the moments is the same formula, but it's got an extra z in there. So that's the displacement times the mass, okay, of any particular disk. And then we sum all those disks. That's what the integral does. And we generate the sum of the moments. Okay, so the units on this one, well, we've already analyzed the units on this one. That's grams. And then this one is centimeters. So I'll just write that this one is centimeters, and this whole thing we did down below, that's grams. Okay, so then this one winds up as centimeter grams, which is a weird unit, you have to admit. Okay, but then that whole thing, since it's dividing, you wind up with centimeters. And of course, that's what we want. We want to know how far to go out from the origin, how far up from the origin to get to this z bar value. So we need a length. All right, so we need to do quite a few things, but let's go and get the limits of integration. Okay, so what does it say? It's got a radius of 7. So that means that if any one of these out to the edge is going to be 7, that's going to be 7 here. That's going to be negative 7 back there. This length is going to be 7. That length is going to be 7. They're all going to be 7. All right, so when I start drawing and getting you to remember some integral calculus volume scenarios, I'll be drawing a disk here, and the placement of that disk will be anywhere from 0 to 7. So those are going to be the limits of integration. Okay, great. Now, it says that the density is constant. So these deltas here are constants. So they can be pulled out of the integral. And once they get pulled out of the integral, they actually cancel each other out, so that they become really irrelevant. And then that makes total sense, because if there's uniform density, then the center of mass is going to be independent of whatever that density is. It's not going to play a role. If it's a foam hemisphere, it's going to balance in the same place as if it's a lead hemisphere. It doesn't really matter. Okay, it doesn't matter at all. Okay, so then I'm going to go ahead and kill those off, right? Having had this conversation, that and that are going to just cancel each other out. Okay? Sounds good. It's money. Had to say. All right, so then let's go on to look at this bottom integral. That's I guess no longer representing the total mass, because we just pulled out the density there, but instead it's representing the volume. Density times volume is mass. So this now represents the volume. I'm going to go find the volume. Okay, so let's go get the volume of this hemisphere. Okay, so pulling you back to a lesson from months ago, let's get the volume of the ith disk. So the volume of the ith disk. Well, I need to draw the ith disk. So I'll pull that one out. Guess it doesn't matter. And then we'll do another one. Oh, sweet. That's good. That's looking like a disk to me. Okay, so there it is. And all right, so what do we have? We got a couple of things to label. We're going to label delta z, this little teeny tiny thing right there. And then, in order to find the volume of this, we need to know its radius. Okay, so that's going to get lost in here. So let's go and do that in a different color. And I'm going to call that R. Okay, R sub I really would be a great thing to do. So that's the radius of the ith disk. And of course, there's going to be infinitely many such disks, and they're going to go from radius 7 to radius 0. Okay, so the volume of this ith disk is pi r sub I squared delta z. Okay, pi r squared being the surface area. Well, yeah, I suppose we can think about the surface area there. And then delta z being the thickness of the cylinder. Okay, now then, we need this in terms of z, right? Because this is going to get integrated with respect to z. This r is the problem. So we need to go off to the side. And we need to find a link between r and z. Okay, so that turns out to not be too bad. And I'm going to do that by building a Pythagorean scenario. All right, I'm going to build this Pythagorean argument right here. We got a right triangle. And this hypotenuse is going from the center all the way to the edge. And so then we know the radius of this is 7. So I'm going to give that length 7. And then this is that changing value. You know, it depends upon where we are. as we slide from 0 to 7. So I'm going to call that z, or z sub I if you want. And then this is the rest of it up there, that little section, 7 minus z. Okay, so the link is in this right triangle setup, and we have that r squared plus z squared is equal to 7 squared. All right, so if we put in our r sub I, that's probably better since I did it over here. All right, so then we need to swap out r sub I squared, and that is 49 minus z sub I squared. Okay, so now I've got the volume of the ith disk. It is pi, and then 49 minus z sub I squared delta z. Okay, so then the volume of the hemisphere is, and we'll skip the usual trilogy, that's the integral of pi 49 minus z squared dz from 0 to 7. Okay, so on this problem, unlike what I'm going to do on the next problem, I'm going to use the calculator, and let's see, I've typed that whole thing in, and it's 686 pi over 3. Okay, so that is my current denominator for a z bar. Now that's after I canceled out the density. Okay, so let's then not lose sight of that, right? So this is where we are. We've got z bar equals, and then we've got 686 pi over 3. All right, so clearly we need to go get the numerator, and that's just a little bit tougher of an integral, but not so bad. All right, so I'm just going to draw a clear demarcation there, and now I'm working on the sum of the moments. Okay, so that is the integral of z. And then you notice that it's exactly the same thing that I had here before. So it's this integral with an extra z in it. So this time I'll just do it a little differently. I'll pull out that constant, and then we've got 49 minus z squared dz that needs to be evaluated from 0 to 7. All right, and then again, I'm gonna go straight to the calculator, unlike what I'm going to do on the next problem, where I'm going to do it all by hand. And then the reason I'm doing that is just because it's easy, right? I mean, it's to distribute the 7, some reverse power rule. So it's pretty tedious, and it's not really reminding us of anything. All right, so let me get my calculator number for you. Okay, so that number is 2401 pi over 4. And I'll put that up here. Okay, so that's kind of an annoying setup there, but let's see what we got. We got 2401 pi over 4 times this guy flipped, which is 3, and then that's 686 over pi. All right, let's go cancel here. We'll go cancel there. And my guess is that there's something super nice that goes into both of those, but I don't know what that is. Let me see if I can just divide those two and see if that's a good clue for me. 7 halves is what it says. Okay, so I divided those two, so evidently there's some number that's big that goes into that one 7 times, and this one only 2 times. So I guess that number is 343. Okay, so let's see. Does that I think that takes us to the finish line because I can't reduce anything more. That's 21/8 centimeters. Okay, so what is that? That's 8/16. That's 2 and 5/8 centimeters. All right, so let's see if we can feel that. This was a length of 7, so we're going, just past 2.5, and that means the center mass is, somewhere around there. And I can get into that, right? Because it's clearly going to be closer to the origin. And okay, so there you go. That's our first three-dimensional version. Have I answered the question? Find the center of mass. I didn't really list it as an ordered triplet, but it's 0, 0, 2, and 5/8. All right. So taking a quick look at the clock, that's 20 minutes, and I know my next one problem is even going to take a longer amount of time. So I'm going to give you a problem to try on your own, and we'll cut this a little bit short. And looks like there's just the one problem here and the one assignment problem. Okay, so I'll bring that over to you. All right, here you go. This is the problem that I'm going to have you do, and then you're welcome to pop into the meets and the tutorials, no problem. Send emails, and then we'll get going on part 2 after this one.